Before there were stars, before there were galaxies, before there were planets, moons, oceans, mountains, or the first atoms of a living world, there was a universe almost impossible to imagine. Not empty, not dark in the way we understand darkness, not quiet in the way a night sky is quiet. It was a universe without stars because stars had not yet formed. A universe without galaxies because gravity had not yet gathered matter into great spirals and clusters. A universe without atoms because it was still too hot for atoms to survive. A universe without familiar distances, without familiar shapes, without any place that could be called here or there in the ordinary sense. It was not an explosion into space. It was space itself expanding. Everything that would one day become the observable universe was once compressed into an extremely hot, extremely dense state. Not a fireball expanding into a surrounding emptiness, but the beginning of expansion everywhere, with space stretching and cooling as time moved forward. This is what we call the Big Bang. The name sounds sudden, loud, almost violent. But the true idea is stranger and deeper. It does not describe a bomb in the darkness. It describes the earliest hot, dense phase of the universe that physics can trace, the beginning of the cosmic story we can reconstruct from light, matter, motion, and mathematics. What came before it, if before is even the right word, remains unknown. The universe does not give us that answer easily. Our equations can look backward through billions of years. They can describe galaxies rushing apart, light stretched by expansion, the ancient glow of the cosmic microwave background, and the formation of the first elements. But when we try to reach the very first instant, the familiar laws become uncertain. Gravity, quantum physics, energy, and space-time meet in a region where our understanding is incomplete. So the story begins not with certainty, but with a horizon, a boundary in knowledge, a place where the known universe rises out of mystery. Around 13.8 billion years ago, the universe was far hotter and denser than it is today. Space was expanding. The temperature was immense. Energy filled everything. The universe was not yet filled with stars, but with conditions so extreme that matter itself had not yet taken the familiar forms we know. There were no planets, no dust, no carbon, no iron, no water, no stone, no sky. Only an early universe of energy, particles, fields, and expansion. In the earliest fractions of a second, according to one of the leading ideas in modern cosmology, the universe may have gone through a period called inflation. In this brief and extraordinary phase, space expanded at a breathtaking rate, faster than any ordinary expansion we can easily picture. It was not that objects were racing through space faster than light. Instead, space itself was stretching, carrying regions apart. Inflation is not fully understood. Scientists do not yet know exactly what powered it, or whether our description of it is complete, but it explains several deep features of the universe we observe today. It helps explain why the universe looks so smooth on large scales, why distant regions have nearly the same temperature, and why the geometry of the universe appears so close to flat. It also gives a possible origin for the tiny irregularities that later became everything. During inflation, quantum fluctuations, tiny variations in energy at the smallest scales, may have been stretched across cosmic distances. What began as almost unimaginably small ripples became faint differences in density across the young universe. Some regions were only slightly denser than others. Some were slightly less dense. The differences were tiny, but gravity is patient. Those small irregularities would one day become the seeds of galaxies, the seeds of galaxy clusters, the seeds of the cosmic web. The first quiet hints of structure in a universe still too hot to shine with stars. At first, the universe was so energetic that the forms of matter we know could not yet exist. The temperature was too high for atomic nuclei. too high even for protons and neutrons in the way we usually imagine them. The universe was filled with a hot, dense sea of fundamental particles and radiation, constantly interacting, appearing, disappearing, transforming. Quarks, electrons, neutrinos, photons, antimatter particles, and other ingredients of the early universe moved through a state of almost unimaginable heat. There was no solid matter, no molecules, no atoms, no nuclei, only a luminous, violent simplicity. But expansion changed everything. As space grew, the universe cooled. This cooling was not like an object placed in a cold room. There was no outside room. The universe cooled because the fabric of space expanded, stretching radiation and lowering the energy of particles. With each tiny moment, the cosmos became a little less extreme, a little more able to form structure. One of the great mysteries of this early time is why matter survived at all. In the hot early universe, matter and antimatter should have been created in nearly equal amounts. Matter and antimatter destroy each other when they meet, converting into energy. If the early universe had made them in perfectly equal quantities, then almost everything might have vanished into radiation, leaving little behind to form stars, planets, or life. But matter won. Only slightly. For reasons still not fully understood, there was a tiny excess of matter over antimatter. Perhaps only one extra matter particle for every vast number of matter, antimatter pairs. Almost everything annihilated, but that small leftover became the material universe. The stars, the galaxies, the planets, the atoms in every ocean, every rock, every living cell, all of it may exist because of a tiny imbalance in the earliest moments of time. A small asymmetry, a slight preference. A whisper in the laws of nature. As the universe continued to cool, quarks became confined inside protons and neutrons. The universe had passed from a sea of freer particles into a state where the building blocks of atomic nuclei could begin to exist. Protons and neutrons formed in the hot plasma, moving through space with radiation and other particles. Still, this was not yet a universe of atoms. It was too hot for electrons to settle around nuclei, too hot for light to travel freely, too dense and energetic for transparency. The universe was like a glowing fog, but far more extreme than any fog on Earth. Light existed, but it could not move freely for long. Photons were constantly scattered by charged particles. Every path was interrupted. Every beam was redirected. The universe was opaque, filled with radiation trapped in a dense plasma. There was light everywhere, but no clear view, no darkness, no stars, no space through which light could travel undisturbed, only a hot, luminous mist. Within the first few minutes, the universe cooled enough for a brief and important era called Big Bang nucleosynthesis. Protons and neutrons began to combine into the first light atomic nuclei. Hydrogen nuclei, which are single protons, were abundant. Helium nuclei formed as protons and neutrons fused together. Tiny traces of lithium and other light elements also appeared. This early nuclear furnace did not last long. The universe was expanding and cooling too quickly. After roughly the first several minutes, conditions were no longer hot and dense enough for widespread nuclear fusion to continue. The universe had created mostly hydrogen and helium, with only a small trace of lithium. The heavier elements would have to wait. There was no carbon yet, no oxygen, no silicon, no iron, no gold. Those elements would be born much later, inside stars and in the violent deaths and collisions of stars. The early universe made the simplest ingredients first, then left gravity and time to do the rest. Hydrogen. Helium. A little lithium. A beginning. It is strange to imagine a universe with no heavy elements. No rocky planets could form from hydrogen and helium alone. No mountains, no oceans, no metal, no bones, no dust grains drifting through cold nebulae, no familiar chemistry. The universe had matter, but not yet richness. It had the first nuclei, but not the elements that make worlds complex. The early cosmos was simple, but not empty. It was filled with the raw material of stars. Hydrogen would become the main fuel of the first stars. Helium would be the ash of their burning and the companion of hydrogen in the great clouds from which galaxies would grow. The simple chemistry of the early universe was not the end of the story, but the first quiet layer. For hundreds of thousands of years, the universe remained a hot plasma. Atomic nuclei existed, especially hydrogen and helium nuclei, but electrons were still free. They had not yet settled into stable orbits around nuclei to form neutral atoms. The universe was filled with charged particles, and charged particles scatter light. Photons could not travel across great distances without being interrupted. The universe glowed, but it was blind to itself. If there had been eyes, they could not have seen far. Every direction would have been filled with a bright, dense haze. No stars, no galaxies, no blackness between lights. Only the radiant opacity of the young cosmos. During this time, dark matter was also present, silently shaping what would come later. Dark matter does not shine or absorb light in the ordinary way. It does not interact strongly with radiation, and that made it important in the early universe. While ordinary matter was tightly coupled to light in the hot plasma, dark matter could begin to gather under gravity more freely. It formed the invisible scaffolding. Slightly denser regions of dark matter pulled more dark matter toward them. The effect was tiny at first, but over time these regions became gravitational wells. Ordinary matter, once it was free to fall more easily, would later gather into these wells. The earliest galaxies would form where gravity had already begun, preparing the ground. Dark matter was not seen. It did not shine, but it helped shape the future architecture of the cosmos. The universe was becoming a place where structure could one day appear. Still, the ordinary matter remained tied to radiation. Photons pushed and scattered. Electrons moved freely. The plasma rippled with sound waves, not sound as human ears would hear it, but pressure waves moving through the hot early universe. These waves left marks in the distribution of matter and radiation, patterns that can still be studied today in the cosmic microwave background and in the large-scale arrangement of galaxies. The early universe had a kind of music, not sound in air, not sound in space as we know it, but oscillations in a plasma of matter and light, rhythms in the first fire. Those rhythms would leave a faint imprint on everything. As the universe expanded, the temperature continued to fall. The radiation lost energy. The plasma thinned. The nuclei and electrons moved more slowly. The long, bright fog approached a transformation. After about 380,000 years, the universe had cooled enough for electrons to combine with atomic nuclei. Hydrogen and helium atoms could finally form. This era is called recombination, though it was really the first widespread combination of electrons with nuclei. The change was profound. Once electrons were bound inside neutral atoms, they no longer scattered photons so strongly. Light was released. The universe became transparent. For the first time, photons could travel freely across space. A great glow, once trapped in the plasma, streamed outward in every direction. That light has been traveling ever since, stretched by the expansion of the universe from hot, visible and infrared light into cold microwaves. Today, we detect it as the cosmic microwave background, the oldest light we can observe directly. It is the afterglow of the early universe, a fossil of the time when the cosmos became transparent, a wall of ancient light surrounding every direction we look. When we study the cosmic microwave background, we are not seeing the Big Bang itself. We are seeing the universe as it was about 380,000 years after the hot beginning, when light last scattered from the primordial plasma and began its long journey through space. It is like seeing the surface of a fog as it clears. Behind that surface lies the earlier, opaque universe, where light could not travel freely. The cosmic microwave background is almost uniform. It has nearly the same temperature in every direction. This tells us that the early universe was extraordinarily smooth. But it is not perfectly uniform. There are tiny temperature variations, small differences from place to place. Some regions were slightly hotter, some slightly cooler. These differences are extremely small, but they are among the most important marks in all of science. They are the fingerprints of the early universe, the seeds of future structure. Where matter was slightly denser, gravity would slowly gather more matter. Where matter was slightly less dense, regions would become more empty. Over billions of years, those tiny differences would grow into galaxies, clusters, filaments, and voids. The entire cosmic web was hidden in the faint mottling of ancient light. Every galaxy began as an almost imperceptible irregularity. Every cluster began as a slightly deeper gravitational place. Every future star, planet, and living world depended on the fact that the universe was smooth, but not perfectly smooth. If the early universe had been perfectly uniform, gravity would have had no preferred places to gather matter. No stars would form, no galaxies would arise. If it had been too irregular, matter might have collapsed too violently, perhaps forming a universe very different from our own. Instead, the universe carried just enough unevenness, a quiet imperfection, a cosmic grain. From that grain, structure would grow. After recombination, the universe entered a long, strange era often called the Cosmic Dark Ages. The name is fitting, but it must be understood carefully. The universe was not empty. It was filled mostly with hydrogen and helium gas, dark matter, radiation, and the growing pull of gravity. But there were no stars yet, no galaxies shining with billions of suns, no starlight pouring through space. The cosmic microwave background filled the universe, but as space expanded, that ancient glow stretched and cooled, fading into longer wavelengths. Visible light disappeared. The universe became dark. Not because nothing existed, but because nothing had yet ignited. This darkness lasted for a long time, tens of millions of years, perhaps hundreds of millions before the first stars fully transformed the cosmos. During this era, the universe was quiet in a new way. The hot plasma had become neutral gas. Photons traveled freely, but there were no bright sources of new visible light. Hydrogen atoms drifted through expanding space. Dark matter gathered into larger and larger halos. Gravity worked slowly, drawing matter into the places where density was a little higher. The universe waited. But it was not a passive waiting. It was a hidden preparation. Dark matter halos deepened. Gas began to fall into them. Slightly denser regions attracted more matter. The first faint architecture of the cosmic web began to emerge. Sheets, filaments, and knots slowly took shape, not yet lit by stars, but already present as differences in density. Imagine a universe without stars, but not without form. A universe where the map is invisible because nothing shines. A universe where gravity is drawing outlines in darkness. The first galaxies did not appear all at once. They grew from the gradual collapse of matter into dark matter halos. Gas fell inward. As it compressed, it heated. To form stars, gas needed to cool and fragment. The first stars would form from nearly pristine hydrogen and helium, without the heavier elements that later help gas clouds cool efficiently. Those first stars were different from many stars today. They may have been massive, hot, and short-lived. They belong to a generation that no longer exists, often called population 3 stars. They were born from the simple matter made in the Big Bang, before carbon, oxygen, iron, and dust enriched the universe. But that belongs mostly to the next part of the story. For now, in the Dark Ages, those first stars are still approaching. not yet born, only implied, only promised by gravity. The darkness after the cosmic microwave background is one of the most haunting eras in cosmic history. It is not the beginning, and not yet the age of light. It is a middle silence. The universe has cooled enough to become transparent, but not enough structure has collapsed to make stars. Light from the beginning is fading into the microwave background, and new light has not yet appeared. Between the first glow and the first stars there is a long night. In that night, everything familiar is still absent. No Milky Way, no Andromeda, no solar system, no Earth, no atoms heavier than the lightest few, except in tiny traces, no planets of stone, no oceans under skies. No life looking upward, only hydrogen, helium, dark matter, radiation, and the invisible patience of gravity. Yet the future is already written in the faint differences of density. The universe is dark, but it is not without destiny. The regions that will become galaxies are already slightly denser. The regions that will become voids are already slightly less dense. Matter is beginning to sort itself into the great cosmic pattern. The web is forming slowly, invisibly, like frost spreading across a window before dawn. Gravity has no sound. It does not announce itself. It simply changes motion. A hydrogen atom drifting through space feels the pull of a slightly denser region. A dark matter particle moves along the growing slope of gravity. Gas gathers where more gas is gathered. Time passes and the differences grow. The early universe did not need to be sculpted by hand. Its sculptor was gravity. Its material was matter. Its canvas was expanding space, and its first marks were almost too small to notice. This is one of the deepest truths in cosmology. The largest structures in the universe grew from the smallest irregularities. Galaxy clusters spanning millions of light years began as tiny variations in the early plasma. The cosmic web, with its vast filaments and voids, began as faint ripples in density. The places where stars would form were prepared long before stars existed. The universe did not become complex suddenly. It became complex slowly, through cooling, through expansion, through attraction, through imbalance, through the quiet amplification of almost nothing. If we could observe the Dark Ages directly, we would see little invisible light. But in theory, the neutral hydrogen filling the universe carried a subtle signal, a radio whisper known as the 21-centimeter line. This signal is one of the great goals of modern cosmology, to map the era before the first stars and during the time when the first light began to change the universe again. The Dark Ages are difficult to observe because they are truly ancient, and because their signals have been stretched by cosmic expansion. But they are not beyond imagination. They are a hidden chapter, still being sought, still being reconstructed. The universe's first darkness remains partly unseen, not because it was empty, but because it was waiting for light. To understand this era, it helps to remember that the universe is not expanding from one center. Every region sees distant regions moving away as space stretches. The Big Bang did not happen at a point in space. It happened everywhere, in the sense that every part of today's observable universe was once part of that hot, dense early state. There is no direction in the sky where the Big Bang happened. There is no central location we can point to. The beginning is not somewhere far away. It is in the past of everywhere. Every galaxy carries that past. Every region of space was once hotter and denser. Every direction in the sky contains the afterglow. The cosmic microwave background surrounds us because it comes from the early universe in every direction. It is not a shell around a center. It is the light from the time when all space became transparent. When we look at it, we are looking back to a younger version of the universe itself. This makes the beginning deeply intimate. The Big Bang was not over there. The early universe was here too. The atoms in your body, the earth beneath you, the sun above you, the Milky Way around you, all trace their history back to that hot, dense beginning. The matter that would one day become familiar was once part of the same early cosmic fire. The hydrogen in water, the hydrogen in stars, the hydrogen in distant galaxies, all belongs to that first chemistry. The universe began simple, then it learned complexity. The first part of that learning was cooling, then matter survived, then nuclei formed, then atoms formed, then light escaped, then darkness returned. Then gravity began to gather the dark. This sequence is slow when told in words, but the early steps happened with astonishing speed. The first fractions of a second contained transformations beyond ordinary intuition. The first few minutes formed the light nuclei, then hundreds of thousands of years passed before atoms could form. Then tens or hundreds of millions of years passed before the first stars began to shine. Cosmic history is not evenly paced. Some changes happen almost instantly. Others take ages. The universe begins with violent rapidity, then settles into long patience. This rhythm will continue throughout cosmic history. Sudden births, long silences, explosions, waiting, collapse, expansion. It is the pause after the first blow. A pause in which the universe becomes transparent, cools, expands, and prepares the conditions for the first stars. There is mystery in the fact that the universe had to become dark before it could become luminous in the way we know. The first light of the hot plasma had to fade. The cosmic background had to stretch. Neutral atoms had to form. Gravity had to work in the dark before stars could ignite. Darkness was not failure, it was preparation. Without the Dark Ages, the first stars would not have had the quiet time needed to gather. Without the first atoms, gas could not collapse in the same way. Without dark matter halos, ordinary matter would not have had the gravitational scaffolding for galaxies. Without the tiny fluctuations from the early universe, there would have been no preferred places for gravity to begin. Everything depended on what came before. The universe is a chain of conditions. Each era makes the next possible. The Big Bang made the hot, dense beginning. Expansion made cooling possible. Cooling made particles and nuclei possible. Further cooling made atoms possible. Atoms made transparency possible. Transparency made the cosmic microwave background visible to us. Darkness made gravitational collapse possible. Collapse made stars possible. Stars would make heavy elements. Heavy elements would make planets. Planets would make new kinds of chemistry possible. And somewhere, much later, chemistry would become life. But in the first darkness, all of that is still far ahead. The universe is young. The future is immense. The stars have not yet opened their eyes. If one could drift through that early dark universe, there would be no familiar landmarks. The gas would be thin by earthly standards, but spread everywhere. There would be no constellations, because constellations require stars. No galaxies crossing the sky, because galaxies had not yet fully formed. No nebulae glowing with starlight. No planets reflecting sunlight. Only the fading background radiation stretched by expansion. Only neutral hydrogen and helium. Only the invisible pull of dark matter, only the growing unevenness that would become structure. It is a strange thought. The most important things in that era were not visible. The density differences were small. The dark matter did not shine. The future stars were not yet born. The cosmic web was present only as a gravitational tendency. The universe was full of hidden beginnings. This makes the early Dark Ages one of the most mysterious parts of the cosmic timeline. It is an era defined by what is not yet there, but also by what is quietly becoming inevitable. The first star has not formed, but the place where it will form is already gathering. The first galaxy has not assembled, but its dark halo is already growing. The first supernova has not exploded, but the hydrogen that will fuel the star that becomes it already exists. The first carbon atom has not been forged, but the conditions that will one day create stars are taking shape. The first planet has not formed, but the future of planets is already being prepared in the invisible architecture of matter. Everything waits inside the dark. The universe after recombination was colder than before, but still much warmer than the universe today. As millions of years passed, it continued to cool. The cosmic microwave background, once much hotter, stretched into longer and longer wavelengths. The average temperature of the universe fell. Gas clouds began to respond more strongly to gravity. Dark matter halos merged and grew. Small structures combined into larger ones. The first dense regions became deeper. Gas fell inward. At the centers of the earliest halos, the conditions slowly approached the threshold for star formation. But forming the first stars was difficult. The gas was made almost entirely of hydrogen and helium. Without heavier elements and dust, cooling was less efficient. The gas had to rely on simple molecules, especially molecular hydrogen, to radiate away energy and collapse. The process was slow and delicate, compared with later star formation in enriched galaxies. But gravity had time. Gravity always has time. In one region, the gas became a little denser, then denser still. It heated as it compressed, but some energy escaped. The cloud fragmented. A core formed. The first star approached ignition. Across the universe, in separate dark halos, similar processes began. Not everywhere at once, not in a single cosmic dawn, but in scattered beginnings. The first stars likely appeared in isolated pockets, rare at first, then more common. Their light would eventually change the universe, but before that moment there was only the slow preparation. The first darkness was ending before anyone could see it. The universe was about to become luminous again, but not with the smooth glow of the hot beginning. With stars, individual fires, gravity-made lights, the second illumination of the cosmos. There is something powerful in the idea that the universe had two great early lights. First, the light of the hot plasma, trapped and scattered until the universe became transparent. Then, after the Dark Ages, the light of the first stars. The first light was everywhere. The second light was born in places. The first light revealed the universe as a nearly smooth sea. The second light revealed structure. The first light became the cosmic microwave background. The second light began the age of stars and galaxies. Part 1 of the cosmic story belongs to the first light and the darkness after it. Part 2 belongs to the awakening. But before that awakening, let us remain a little longer in the first darkness. The darkness is not empty. It is full of hydrogen atoms drifting through space. Each atom simple, one proton, one electron. Some helium atoms too, with their nuclei formed in the first minutes. Tiny traces of lithium. Neutrinos streaming almost freely through the cosmos, relics from the earliest times. Photons from the cosmic microwave background, traveling through expanding space. Dark matter forming halos, gravity deepening the faint ripples left from the beginning. No planets, no dust, no heavy elements, no life. But the future is not absent, it is encoded. The universe at this stage is like a field before dawn, too dark to see the shapes clearly, but already containing every hill and hollow that sunrise will reveal. The cosmic microwave background is the last visible surface of the hot early universe, but it also serves as a map of what would come later. Its tiny temperature differences show where the seeds of structure lay. Modern satellites and observatories have measured those patterns with extraordinary precision. From them, scientists can infer the age of the universe, its composition, its geometry, and the initial conditions from which galaxies formed. In that faint microwave glow, the universe left a message from 380,000 years after the beginning, a message written before the first star. It says the universe was hot. It says the universe was dense. It says the universe was smooth, but not perfectly smooth. It says dark matter and ordinary matter were already arranged in tiny variations. It says the galaxies were coming. The cosmic microwave background is sometimes called a baby picture of the universe, but even that phrase is too simple. It is more like a fossilized light field, a record of a transition, a moment when the cosmos became transparent. It is not a picture of objects. It is a picture of conditions. No stars appear in it, no galaxies, no planets, only the pattern from which they would grow. The fact that we can observe it at all is extraordinary. Light released when the universe was only hundreds of thousands of years old still reaches us today. It has crossed almost the entire history of time. Expansion has cooled it to just a few degrees above absolute zero. Sensitive instruments can detect it as a faint microwave glow coming from every direction. Everywhere we look, we see the ancient afterglow. We are inside the remnant light of creation. But as part one moves toward its ending, the glow fades into the background. The universe becomes colder and darker. The ancient photons continue traveling, but they no longer fill the universe with visible brilliance. Hydrogen gas dominates the ordinary matter. Gravity continues gathering. The darkness deepens. And somewhere, in one of the first small halos, a cloud begins to collapse. There is still no star, but there is a center, a place where gas falls inward, a place where pressure rises, a place where the first cosmic fire is preparing to ignite. The universe has traveled from unimaginable heat to cooling plasma, from particles to nuclei, from nuclei to atoms, from opacity to transparency, from the first light to the first darkness. It has become a place where light can travel, where matter can gather, where gravity can build. Everything is ready, but nothing has yet shone from within the darkness. The first stars will change that. They will tear open the dark ages. They will forge new elements. They will begin the long transformation from a simple universe of hydrogen and helium into a rich universe of galaxies, planets, chemistry, and life. But for now, the universe remains in its ancient night, a vast expanding darkness filled with invisible structure. A silence after the first glow, a cosmos waiting for its first stars. In the long darkness after the first light had faded, the universe waited. There were no stars yet, no galaxies brightening the distance, no planets moving around newborn suns. No dust clouds glowing in red and blue. No constellations, no nebulae, no spiral arms, no clusters of ancient stars. The universe had become transparent, but it had not yet become luminous. The ancient light released when the first atoms formed was still traveling through space, but expansion had stretched it, cooled it, softened it into the background. What had once filled the cosmos with a hot glow was slowly becoming the faint afterglow we now call the cosmic microwave background. Around it, through it, beneath it, matter drifted. Hydrogen, helium, a trace of lithium, dark matter, radiation. Neutrinos moving almost untouched through the young universe. And gravity, patient and invisible, beginning its work. The universe was no longer the blinding plasma of its earliest age. Electrons had joined nuclei, neutral atoms had formed, light could finally travel freely. But with no stars to create new light, the cosmos entered an era of deep and ancient darkness. It was not empty darkness, it was fertile darkness, the darkness of a field before anything has grown, the darkness of a seed beneath soil, the darkness of a universe gathering itself. The tiny variations left from the earliest moments were now becoming important. Some regions were slightly denser than others, not by much, barely enough to imagine. But gravity needs only a beginning. Where matter was a little denser, it pulled in more matter. Where dark matter had gathered into invisible halos, ordinary gas began to fall. Slowly, across millions of years, the first structures deepened. Dark matter did not shine. It did not scatter light in the way ordinary matter did. It did not form glowing clouds or visible filaments, but it shaped the path of everything that could shine later. It gathered first, making the gravitational wells into which hydrogen and helium could fall. In the darkness, unseen scaffolding formed. Vast halos of dark matter grew by attraction and merger. Smaller halos joined larger ones. Threads of density began to stretch through space. The first faint outline of the cosmic web appeared not as light, but as gravity. If there had been a way to see mass itself, the universe would not have looked empty. It would have looked like a faint growing network, denser knots connected by filaments, great regions with less matter slowly becoming emptier. The first hints of future galaxies gathering in the invisible frame. But to ordinary light, it was still night. There was no star to reveal the web, no galaxy to trace the filaments, no supernova to scatter heavy elements, only gas falling inward, only darkness becoming uneven, only gravity turning small differences into future worlds. In some places, hydrogen and helium gas began to collect inside dark matter halos. As gas fell inward, it compressed. As it compressed, it heated. Heat creates pressure, and pressure resists collapse. For a star to form, gas must find a way to cool, to lose energy, to continue falling inward until its center becomes dense and hot enough for nuclear fusion. In the modern universe, star-forming clouds contain dust and heavier elements. Carbon, oxygen, silicon, iron, and many other atoms help gas cool. Dust grains shield molecules and allow clouds to fragment into many stars. But the first star-forming gas had almost none of these ingredients. It was almost pure hydrogen and helium, with only the faintest trace of lithium from the first minutes of cosmic history. So the first stars formed under different rules. They were born from simpler matter. They were born before the universe had metals, before planets, before dust-rich nebulae. They were born in a cosmos still chemically young. Molecular hydrogen may have helped the gas cool enough to collapse. In the deepest parts of the first halos, clouds contracted. Their centers grew denser. The gas fell inward under its own gravity. Temperature and pressure rose. For millions of years, the dark universe had been preparing. Then, somewhere in the blackness, a core became hot enough. Hydrogen began to fuse. The first star ignited. There was no eye to see it, no planet beneath it, no dust cloud reflecting its light, no creature looking upward. But the universe had changed forever. For the first time since the fading of the primordial glow, light was being made inside an object. Not the trapped light of a hot plasma, not the cooling afterglow of the Big Bang. This was starlight, a new kind of fire, a gravity-born light. The first stars are still mostly theoretical. Astronomers have not yet observed an individual first-generation star with certainty. But the physics of the early universe tells us they must have existed. They are often called population 3 stars, a name that sounds backward because astronomers named stellar populations in the order they were discovered, not the order they were born. These first stars may have been very massive, far larger than the Sun. Without heavier elements to cool the gas efficiently, the first collapsing clouds may have formed stars that were hotter, brighter, and shorter-lived than most stars today. Some may have lived only a few million years, burning furiously in the dark before ending in violent deaths. Their light began the cosmic dawn. At first, the dawn was not everywhere. It did not sweep across the universe in a single moment. The first stars appeared in scattered regions, rare and isolated, little islands of light in the immense darkness. Around each young star, ultraviolet radiation streamed outward, striking the surrounding hydrogen gas. The light was powerful enough to tear electrons away from hydrogen atoms, ionizing the gas and creating growing bubbles in the dark. One star became a bubble of light, then another, then clusters of early stars. then the first small galaxies. The dark universe began to fill with glowing wounds. This was the beginning of the epoch of reionization. After recombination, the universe had become mostly neutral, filled with hydrogen atoms. But the first stars and galaxies changed that. Their radiation began breaking neutral hydrogen apart again, separating protons and electrons across growing regions of space. Over hundreds of millions of years, these ionized bubbles expanded and overlapped. Eventually, much of the hydrogen between galaxies became ionized. The universe became transparent to ultraviolet light over larger and larger distances. The Dark Ages came to an end. It was not a peaceful ending. The first stars were intense. Their ultraviolet light was harsh. Their lives were brief. Their deaths were enormous. Yet on the scale of the universe, this violence was also creation. The first stars did something the Big Bang had not done in large amounts. They made new elements. Inside their cores, hydrogen fused into helium. In the most massive stars, helium could fuse into carbon. Carbon could lead to oxygen, neon, magnesium, silicon, sulfur, and eventually iron in the cores of later massive stars. The first generation began the long chemical transformation of the cosmos. The early universe had been simple. Stars made it complex. When massive stars exhausted their fuel, their cores collapsed. Some exploded as supernovae. Some may have collapsed directly into black holes. In the explosions, newly forged elements were thrown into space. The surrounding gas, once nearly pure hydrogen and helium, became enriched. For the first time, carbon drifted through interstellar space. Oxygen, silicon, iron, elements needed for dust, rock, water, planets, and life. The death of the first stars seeded the next stars. The universe learned to recycle. A star formed from simple gas. It burned. It forged heavier atoms. It died. It scattered those atoms into the darkness. Then new clouds gathered from enriched gas, and new stars formed with ingredients the first stars never had. With each generation, the universe became more chemically rich. Starlight was no longer only light. It was alchemy. The first stars also left behind black holes. Some may have been the seeds of larger black holes that grew over cosmic time. Gas falling into black holes released enormous energy. In the centers of early galaxies, black holes may have fed rapidly, becoming quasars, brilliant beacons visible across enormous distances. Some of the most distant quasars we observe today appear so early in cosmic history that their existence remains a major challenge and clue. How did supermassive black holes grow so large so quickly? Did they begin from the remnants of the first stars? Did some form from the direct collapse of massive gas clouds? Did early galaxies feed them with extraordinary efficiency? The answer is still being studied, but their light tells us something important. In the young universe, structure was already growing fast. Galaxies were forming. Gas was falling inward. Black holes were feeding. The darkness had not merely ended, it had become active. Across the cosmos, the first galaxies began to gather. They were not like the great spiral galaxies we see nearby today. Many early galaxies were smaller, irregular, turbulent, full of gas and rapid star formation. They grew by pulling in gas from the cosmic web and by merging with other young galaxies. In the early universe, collisions and mergers were common. Small structures joined into larger ones. Dark matter halos merged. Stars were scattered and rearranged. Gas compressed and ignited new bursts of star formation. Galaxy formation was not a single event. It was a long assembly. A process of gathering, merging, cooling, forming stars, losing gas, gaining gas, growing black holes, and being shaped by environment. The first galaxies were the universe, learning to organize light. Each one held stars, gas, dark matter, and sometimes growing black holes. Each one was a gravitational island forming inside a larger web. Together, they began to illuminate the architecture that had been hidden during the Dark Ages. The cosmic web became visible, not all at once, not completely, but through the galaxies that formed along its filaments and knots. Matter was not evenly distributed. Gravity had amplified the early ripples. Dense regions became denser. Underdense regions became emptier. Galaxies formed where dark matter and gas gathered. Clusters formed where many galaxies fell together. Filaments stretched between them like luminous threads. Voids opened in between, vast regions with comparatively few galaxies. The universe became a web of light around darkness. Filaments, clusters, walls, voids. A structure so vast that individual galaxies became like dust motes along its strands. The cosmic web is one of the grandest patterns in nature. It is not built from solid material, but from gravity and time. Its threads can stretch across hundreds of millions of light years. Its knots can contain thousands of galaxies. Its voids can be so large that entire galaxy clusters seem sparse inside them. This web had its origin in the tiniest differences of the early universe. The almost invisible imperfections in the cosmic microwave background became the largest structures ever known. A faint ripple became a filament. A slightly denser region became a cluster. A slightly emptier region became a void. The universe turned subtlety into architecture. As galaxies grew, their stars lived and died. The first stellar generations enriched the gas. Later generations formed with heavier elements. Stars became more varied. Smaller stars could form more easily in cooling clouds. Dust grains appeared. Molecules became more abundant. The raw materials of rocky planets began to accumulate. But before planets could exist, the elements had to be made. The Big Bang made mostly hydrogen and helium. Stars made the rest. This is one of the most profound facts in the story of the universe. The carbon in living cells was forged in stars. The oxygen we breathe was made by stellar fusion and scattered by stellar death. The calcium in bones, the iron in blood, the silicon in rock, the gold in buried veins, the uranium inside Earth, all belong to cosmic history. Some elements form inside stars during their lives. Some form in supernova explosions. Some heavy elements are created in neutron star mergers and other extreme events. The full story of element formation is complex, but the essential truth remains. The universe had to pass through stars before it could make planets like Earth. The first stars made the universe chemically possible. Their deaths made the next worlds imaginable. In one galaxy after another, this enrichment continued. Gas clouds formed stars. Stars returned material to space through winds and explosions. New stars formed from enriched gas. Around some of them, disks of dust and gas gathered. In those disks, grains stuck together, becoming pebbles, rocks, planetesimals, and eventually planets. The path from the Big Bang to a planet is long. First expansion, then cooling, then nuclei, then atoms, then darkness, then stars, then heavy elements, then dust, then disks, then worlds. Every planet is a late consequence of the first stars. Every rocky surface is built from ancient stellar ashes. As the universe matured, galaxies became larger and more organized. Some grew into spirals with rotating disks, glowing arms, and central bulges. Others became ellipticals, vast clouds of older stars with little gas remaining. Some were distorted by collisions. Some were stripped in clusters. Some remained small and faint. Galaxy evolution followed many paths. The Milky Way was one of these growing galaxies. It did not appear all at once. Our galaxy began forming more than 13 billion years ago, as early stars and gas gathered inside a dark matter halo. Over time, it grew by accreting gas and merging with smaller galaxies. Its halo filled with ancient stars and globular clusters. Its disk formed and changed. Its spiral structure emerged. Its central bar developed. Its satellites gathered around it. Streams of stars from disrupted dwarf galaxies still trace old mergers in the galactic halo. The Milky Way is not a static island. It is a history. A record of collisions, star formation, gas flows, and dark matter. It is still changing now. From the outside, if we could see it from far beyond its disk, the Milky Way would appear as a barred spiral galaxy, perhaps 100,000 light-years across, filled with hundreds of billions of stars. Its disk would glow faintly blue and white in star-forming regions, red in hydrogen clouds, golden in older stellar populations. Dust lanes would wind through its spiral arms. At the center, a supermassive black hole would sit in the crowded heart of the galaxy. But for billions of years before the Sun existed, the Milky Way was already forming stars. Generations of stars lived and died in its arms and earlier structures. They enriched the gas with heavy elements. They seeded the galaxy with dust. They prepared the material from which future star systems could form. The Sun was not among the first stars. It is a later star, born in a universe already rich with the products of earlier generations. This matters. If the Sun had formed too early, before enough heavy elements existed, there may not have been enough material to build rocky planets like Earth. But by the time the Sun formed, about 4.6 billion years ago, the Milky Way had already been chemically enriched for billions of years. The gas cloud that gave birth to the solar system contained hydrogen and helium, but also carbon, oxygen, silicon, iron, magnesium, nickel, and many other elements. The Sun was born from recycled cosmos. Its planets were built from matter older than the Sun. Some atoms in Earth had once been inside stars that died before the solar system existed. Some may have come from supernovae, some from the winds of aging stars. Some heavy elements may have come from neutron star mergers long before Earth formed. Our solar system is not the beginning of matter. It is a late arrangement of ancient ingredients. The birth of the Sun happened inside a cold molecular cloud, a region of gas and dust within the Milky Way. Something disturbed part of the cloud, perhaps the pressure from nearby stars, perhaps a shock wave, perhaps ordinary gravitational instability. A region collapsed. As it collapsed, it spun faster. Most of the mass gathered into the center, becoming the young Sun. The remaining material flattened into a rotating disk. Inside that disk, dust grains collided and stuck. Pebbles formed, then rocks, then planetesimals, then planetary embryos. Near the young Sun, where it was hot, metals and silicates could condense into rocky worlds. Farther out, beyond the frost line, ices could survive, allowing giant planets to grow. Jupiter, Saturn, Uranus, and Neptune took shape in the colder outer disk. Moons formed, were captured, or emerged from impacts. Comets and asteroids remained as leftovers of formation. The solar system was born from the same broad process that had been unfolding across the universe for billions of years. Stars forming from gas, planets forming from disks, worlds emerging from dust. On Earth, the story became stranger still. A rocky planet cooled. A crust formed. Water gathered. Atmosphere changed. Chemistry became complex. At some point, life began. The exact origin of life remains unknown, but its ingredients were cosmic. The atoms were made by stars. The planet was built in a disk around a star. The energy came from sunlight, chemistry, and Earth's interior. Life is not separate from cosmic history. It is one of its outcomes. The universe needed time to become capable of life. It needed stars to forge elements. It needed galaxies to recycle matter. It needed planets to form. It needed stable environments where chemistry could persist. It needed long-lived stars like the Sun. It needed the quiet accumulation of conditions. The first universe was too hot for atoms. The Dark Ages had no stars. The first stars had no rocky planets around them, or at least not planets like Earth. Only after billions of years could worlds like ours exist. This gives the universe a deep narrative shape. At first it was simple. Then it became luminous, then chemical, then planetary, then, somewhere, biological. The universe awakened not in one moment, but in layers. The first stars were one awakening, the first galaxies, another, the first heavy elements, another, the first planets, another, the first life, another. Each layer emerged from the one before it. And each layer was made possible by gravity, expansion, and time. As galaxies continued to evolve, the universe entered what might be called its bright middle age. Star formation reached a peak billions of years ago, when the universe was younger and richer in cold gas. During that era, galaxies formed stars at rates much higher than many do today. The cosmic star formation rate rose, reached a broad peak, and then began to decline, as gas was used, heated, expelled, or locked away. This was the age when galaxies blazed with creation. Massive stars formed in great numbers. Supernovae exploded. Black holes fed. Galaxies collided and merged. Clusters grew. The cosmic web became more pronounced. The universe was alive with transformation. But even in this active age, the future had already begun to change. The expansion of the universe continued. Gravity gathered matter into structures, but on the larger scales, space kept stretching. Galaxy clusters formed and became bound. Groups gathered. But distant regions moved away as the universe expanded. Much later, dark energy would begin to dominate the expansion, changing the long-term fate of cosmic structure. That belongs to the next part of the story. For now, the universe shines. Across the cosmic web, galaxies glow in clusters and filaments. Spiral galaxies turn slowly. Elliptical galaxies hold ancient stars. Dwarf galaxies orbit larger ones. Black holes sleep or feed in galactic centers. Stars are born in cold clouds and die in glowing remnants. Planets form in disks. Some worlds are frozen. Some are scorched. Some drift alone. Some orbit in systems of many planets. Some perhaps carry oceans beneath ice. Some perhaps carry life. The universe has become a place of variety. This variety is the opposite of the early simplicity. In the first minutes, the universe made mostly hydrogen and helium. Now there are galaxies of many shapes, stars of many masses and colors, planets of rock, gas, ice, and metal, moons with volcanoes, oceans, atmospheres, and frozen plains, nebulae rich with dust, black holes from stellar remnants to supermassive giants, clusters containing thousands of galaxies, voids containing almost none. The universe has become textured, not uniform, not silent, not simple. It has become a vast hierarchy of structures, atoms inside molecules, dust inside clouds, clouds inside galaxies. Galaxies inside groups, groups inside clusters, clusters inside filaments, filaments around voids, voids inside the cosmic web, and all of it expanding, all of it changing, all of it descended from the first darkness. The first stars did more than light the cosmos. They ended the universe's chemical innocence. Before them, the cosmos was almost pure. After them, it became mixed with the ashes of stellar interiors. Every later generation of stars inherited that enrichment. Every planet inherited it too. In the atmosphere of a planet, oxygen may drift. In the core of a planet, iron may sink. In the crust, silicon and oxygen may form minerals. In oceans, hydrogen and oxygen may become water. In living things, carbon may form chains and rings, building complex molecules. These are local arrangements, but their origin is cosmic. A carbon atom in a living cell may once have been in the heart of a red giant star. An oxygen atom in water may have been forged in a massive star and scattered in a supernova. An iron atom in a planet's core may have been produced in the life or death of stars. The universe became capable of memory because stars made atoms that could build complexity, and galaxies became the great reservoirs where that complexity accumulated. Inside the Milky Way, the story continued for billions of years. Stars formed in spiral arms. Some lived briefly and exploded. Others, like red dwarfs, would live far longer than the current age of the universe. Gas clouds were stirred by supernova shocks and stellar winds. Magnetic fields threaded the interstellar medium. Cosmic rays traveled through the galaxy. Dwarf galaxies fell inward and were torn apart. The galactic disk evolved. The Sun formed in this mature galaxy. It was one star among many, not near the center, not at the edge, but in the broad disk, far from the violent, crowded core. Around it, planets formed. Earth cooled. The moon stabilized its companion world. The oceans appeared. Continents shifted. Life began and changed the atmosphere. Eventually, organisms looked at the sky, and the universe became aware of its own history through them. But the cosmos did not form Earth because it had a goal. There is no evidence of intention in the large-scale universe. The story is not destiny in the human sense, it is emergence. Given matter, gravity, expansion, nuclear physics, and time, complexity can arise, not everywhere, not always, but in places, in stars, in galaxies, in chemistry, perhaps in life. The universe awakened unevenly. Some regions became rich clusters of galaxies. Some became lonely voids. Some galaxies formed stars rapidly and then quieted. Others continued forming stars for billions of years. Some stars lived fast and died violently. Others burned so slowly that they will shine for trillions of years. The cosmos is not one story moving at one pace. It is many clocks. The clock of a massive star may run for only a few million years. The clock of a sun-like star runs for billions. The clock of a red dwarf may run for trillions. The clock of a galaxy cluster stretches across cosmic time. The clock of expansion runs through everything. Part 2 of the universe is the age of becoming, the age of first light after darkness, the age of stars and galaxies, the age of elements and planets, the age when the universe becomes rich enough to contain observers. But beneath all this brightness, the future is already changing. The same expansion that cooled the early universe still continues. The same space that carried galaxies apart in the beginning is still stretching. For much of cosmic history, matter and gravity shaped the growth of structure. Dense regions pulled in surrounding matter. Galaxies formed, clusters grew. The cosmic web became more distinct. But the expansion never stopped, and eventually, the universe entered a new era. A more mysterious influence began to dominate the larger scales, dark energy. Its full nature remains unknown. We infer it because the expansion of the universe is accelerating. Distant supernovae, the cosmic microwave background, large-scale structure, and other observations all point toward a universe whose expansion is not merely continuing, but speeding up on cosmic scales. Dark energy appears to act like a smooth energy of space itself, or something similar, though its true identity remains one of the deepest unsolved problems in physics. In the bright age of galaxies, dark energy is quiet at first. Matter still shapes galaxies and clusters. Stars still form. Planets still orbit. Black holes still feed. But on the larger scales, dark energy prepares the next transformation. The universe that awakened will not remain forever as it is. Star formation is already declining compared with its peak. Gas is being consumed. Galaxies are aging. Clusters are becoming more isolated from one another as expansion accelerates. In the far future, galaxies beyond our local gravitationally bound region may drift beyond reach, their light stretched and dimmed until they disappear from view. The universe that once became visible may become hidden again, but not like the first darkness. The first darkness came before stars. The final darkness may come after them. Between those two darknesses lies the bright age, the era of stars, the era of galaxies, the era we inhabit, a universe no longer young, not yet old beyond recognition, a universe filled with light, but already carrying the seeds of its fading. The first stars ignited from pristine gas. Their deaths enriched the cosmos. Galaxies assembled. The cosmic web shone. The Milky Way formed. The sun was born. Earth emerged from dust. Life appeared on one small world. Minds looked outward and traced the story backward through light. This is the universe awake, awake with stars, awake with galaxies, awake with chemical richness, awake with worlds, awake with questions. And yet beyond this brilliant middle age, the long unmaking waits. The stars that now shine will not shine forever. Galaxies that now blaze with formation will grow quiet. The expansion that began in the first moment will continue. Dark energy will shape the horizon. The future will open into colder, stranger possibilities. For now, the universe glows. The Milky Way turns in the dark. New stars are still forming in its clouds. Planets still circle young suns. Galaxies still drift along the cosmic web. Light still crosses the vast spaces between them. The afterglow of the Big Bang still fills the background. The ashes of dead stars still become new worlds. And in this luminous interval between the first darkness and the final unknown, the universe tells its longest and most intricate story. It is the story of matter learning to shine, the story of gravity turning ripples into galaxies, the story of stars making the elements of planets and life, the story of a cosmos that began almost featureless, then opened into structure, fire, chemistry, and memory. From the first star in the ancient dark to the great spiral galaxies of the present age, the universe has been waking for billions of years. But every awakening casts a shadow, and every light carries time within it. The first stars were born, and they died. The first galaxies grew, and they changed. The Milky Way formed, and it will not remain forever as it is. Even the brightest age of the universe is temporary. Beyond the age of galaxies lies a longer future, a future of expansion, of fading starlight, of distant horizons, of dark energy, of possible endings still uncertain. The universe has awakened. But one day, on timescales far beyond ordinary thought, it will begin to fade. The universe has awakened. Across the darkness, galaxies shine like islands of fire. Spiral arms turn slowly around hidden centers. Elliptical galaxies glow with the old light of ancient stars. Clusters gather thousands of galaxies together in vast gravitational cities. Filaments stretch between them, tracing the cosmic web across distances so large that ordinary imagination begins to fade. Stars are born in cold clouds. Stars die in nebulae, supernovae, white dwarfs, neutron stars, and black holes. Planets circle in silence. Moons keep their slow orbits. Comets sleep in distant reservoirs of ice. On at least one world, life has opened its eyes and looked back across time, discovering that the universe had a beginning, that stars had ancestors, that galaxies had childhoods, and that even the largest structures are not fixed forever. But the bright age of the universe is not permanent. Nothing in the cosmos remains unchanged. The first stars burned and vanished. The first galaxies merged and transformed. The Milky Way itself is still moving, still evolving, still carrying the sun through its long orbit around the galactic center. Even the stars that seem eternal are temporary fires. They shine because they are spending fuel. They live because they are slowly changing. Their light is not a static possession, but a process. The universe is luminous now, but it will not always be luminous in the same way. Far beyond the scale of human lifetimes, beyond civilizations, beyond the life of the sun, beyond the future collision of galaxies, beyond all familiar measures of time, the universe is moving toward an uncertain fate. It may expand forever into cold darkness. It may, under some possible forms of dark energy, tear itself apart. It may follow a path not yet fully understood. The ending is not yet known. And that uncertainty is one of the deepest mysteries in cosmology. For much of cosmic history, gravity seemed to be the great sculptor. Gravity drew matter together after the Big Bang. Gravity gathered dark matter into halos. Gravity pulled gas into galaxies. Gravity ignited stars by compressing clouds. Gravity built clusters, filaments in the cosmic web. Everywhere matter gathered, gravity was there, bending motion inward. But the universe was also expanding. From the earliest hot, dense state, space itself stretched. At first, the expansion was rapid and the universe was filled with radiation and matter. Gravity acted against the expansion, slowing it. It did not stop it, but it pulled on everything, resisting the outward growth of cosmic distances. For billions of years, the story seemed like a contest. Expansion carried galaxies apart. Gravity gathered matter together. Where matter was dense enough, gravity won locally. Galaxies formed and remained bound. Clusters formed and remained bound. Stars held planets. Planets held moons. But across larger and larger distances, expansion continued. Then, in the late history of the universe, something changed. The expansion began to accelerate. The universe was not merely expanding, it was expanding faster with time. This discovery came from observations of distant supernovae, exploding stars used as cosmic distance markers. Astronomers expected to find that gravity had slowed cosmic expansion over time. Instead, the distant supernovae appeared dimmer than expected, suggesting they were farther away than a slowing universe would allow. The expansion had sped up. Something unknown was driving acceleration. Scientists gave it a name: dark energy. The name is honest because it does not pretend to explain too much. Dark energy is not well understood. It is not dark matter. It does not clump into galaxies the way dark matter does. It is not ordinary energy like light or heat. It appears to be associated with space itself, or with a field that fills space, or with some deeper physics not yet known. In the standard model of cosmology, dark energy behaves like a cosmological constant, an energy density of empty space that remains constant as the universe expands. If this is true, then as matter becomes more diluted by expansion, dark energy becomes more dominant. Galaxies and clusters remain bound locally, but the large-scale expansion accelerates forever. But dark energy may not be so simple. Recent observations continue to test whether it is truly constant or whether it changes over time. The answer matters profoundly, because the ultimate fate of the universe depends on what dark energy is and how it behaves. If it remains constant, the universe may drift toward an endless cold expansion. If it weakens, other futures become possible. If it strengthens in a particular extreme way, the universe could one day end in a big rip. The big rip is not certain. It is not the accepted destiny of the universe. It is a possible fate, one that depends on a special form of dark energy, sometimes called phantom energy. In that scenario, the density of dark energy increases as space expands. Instead of remaining constant, instead of thinning out, it grows more powerful with time. Its repulsive effect becomes stronger and stronger, until it overwhelms not only the gravity between distant galaxy clusters, but eventually the gravity inside galaxies, then inside solar systems, then the forces holding matter itself together. It is one of the strangest possible endings, not a fading away, not a collapse, a tearing. But before that distant possibility, the universe faces a much slower and more certain transformation. The age of stars will fade. Even if there is no Big Rip, the present bright age cannot last forever. Stars are formed from gas, and gas is not unlimited. Galaxies use their cold gas to make new stars. Supernovae and black holes can heat gas or drive it out. Galaxy clusters can strip gas from galaxies. Over time, the rate of star formation declines. The universe has already passed its peak of star formation. Long ago, when the universe was younger, galaxies formed stars more rapidly than they do today. Cosmic noon, the broad era when star formation was most intense, lies billions of years in the past. Since then, the average rate of star birth across the universe has been falling. The stars still form. The Milky Way still gives birth to new suns inside cold molecular clouds. But the great cosmic blaze of star formation is dimming, slowly, almost imperceptibly on human timescales, but truly across the ages. One day, galaxies will contain less cold gas. Star-forming regions will become rarer. The brilliant blue stars, massive and short-lived, will disappear first because they burn their fuel quickly. The universe will lose its brightest young lights. Massive stars live fast, shining with enormous intensity, then dying after only millions of years. When new massive stars stop forming, they vanish quickly from the cosmic scene. The galaxies of the far future will grow redder, older, quieter. Long-lived stars will remain. Stars like the Sun can shine for billions of years, but even they are temporary. The Sun itself is middle-aged now. In about several billion years, it will leave its long, stable phase. It will swell into a red giant, alter or destroy the inner planets, and eventually shed its outer layers, leaving behind a white dwarf. Earth will not remain as it is. The oceans will not remain forever. The familiar solar system is not eternal. Even the Sun, which feels like the most steady thing in our sky, is a temporary star. But after Sun-like stars fade, smaller stars will continue. Red dwarfs, the smallest ordinary hydrogen-burning stars, are the great survivors of the stellar universe. They burn their fuel slowly and efficiently. Some may shine for trillions of years, far longer than the present age of the universe. They are dim, cool, patient stars. In the far future, when larger stars have faded, red dwarfs may provide much of the remaining starlight. Around some of them, planets may still orbit. In their faint warmth, the universe may remain habitable in scattered places for timescales almost beyond imagining. But even red dwarfs are not eternal. Eventually, they too will use their fuel. The last ordinary stars will fade. The age of starlight will end. The universe will enter a deeper twilight. There will be remnants. White dwarfs cooling slowly in the dark. Neutron stars, dense and silent. Black holes, large and small. Planets without suns, frozen and dark. Brown dwarfs, failed stars barely glowing. Dead systems drifting through galaxies that no longer blaze with new formation. Galaxies themselves will continue to change. Stars will pass one another over immense timescales, gradually rearranging orbits. Some stars will be ejected into intergalactic space. Others may fall into central black holes. Galactic structures will loosen and age. The bright spiral arms we know today depend on gas, star formation, and density waves. In the far future, many galaxies may become dimmer, redder, and more diffuse. The Milky Way and Andromeda will not remain separate. They are moving toward each other, drawn by mutual gravity inside the local group. Billions of years from now, the two great galaxies will merge. Their stars are so widely spaced that direct stellar collisions will be rare, but their shapes will be transformed. Gas clouds may collide and trigger star formation. Their central black holes may eventually spiral together. The result may be a larger, more elliptical galaxy, sometimes imagined as Milkomeda. though no one will be there in the ordinary human sense to see it from Earth as it is now. This future galaxy will remain gravitationally bound. Dark energy will not pull apart bound structures if it behaves like a cosmological constant. The local group, bound by gravity, may remain together while more distant galaxies drift away. Over immense time, galaxies outside our local gravitational neighborhood will recede faster and faster. Their light will be stretched to longer wavelengths. They will become dimmer, redder, harder to detect. Eventually, many will pass beyond the cosmic event horizon, not because they cross a physical edge, but because the accelerated expansion of space prevents their future light from ever reaching us. The universe will become lonely. Observers in the far future, if any exist, may see far fewer galaxies than we do. The rich cosmic web that modern astronomy maps may fade beyond reach. The evidence of the expanding universe may become harder to recover. The cosmic microwave background will stretch to wavelengths so long and temperatures so low that it may become practically undetectable. The distant universe will be hidden by expansion. Civilization born in the far future might look out and see only its local galaxy. It might think that the universe is an island of stars surrounded by empty darkness. The great cosmic history might be concealed. This is one of the quiet tragedies of accelerating expansion. The universe does not merely grow older, it hides its own past. Today, we live at a fortunate time for cosmology. The cosmic microwave background is still detectable. Distant galaxies are still visible. The expansion history can still be reconstructed. The cosmic web can still be mapped. The universe is old enough to contain stars, planets, and observers, but young enough that the evidence of its beginning remains accessible. This may not always be true. The future universe may become scientifically poorer, not because intelligence fails, but because the evidence fades beyond horizons. The bright age is also an age of knowledge, and knowledge, like starlight, may have a cosmic window. As expansion accelerates, the larger scales drift away. But within bound systems, life continues according to local physics. Stars age, planets orbit, black holes accrete and merge, galaxies settle, the universe becomes darker by degrees. This is the path often called the Big Freeze, or heat death. It is not an explosion, not a sudden end, it is a long fading. In this future, expansion continues. Stars gradually burn out, new stars become rare and then cease. Stellar remnants cool. Black holes dominate the remaining energetic processes. Entropy increases. Useful energy becomes harder to extract. The universe approaches a state of cold, thin darkness, with matter spread out and activity greatly diminished. It is an ending of exhaustion. A universe not destroyed, but emptied of contrast. No great rip, no collapse, only the slow loss of usable energy. But the Big Freeze is not the only possible fate. If dark energy changes with time, the future changes with it. If dark energy weakens enough, expansion might slow. In some models, if conditions allowed, gravity could eventually reverse expansion, and the universe could collapse in a big crunch, though current evidence does not show that this is likely under the standard model. If the universe collapsed, galaxies would be drawn back together, the cosmic microwave background would heat again, and the cosmos would approach an extremely dense final state. Some speculative ideas imagine a bounce, where collapse leads to a new expansion, but these ideas remain uncertain. Another possibility is vacuum decay. If the vacuum state of the universe is not truly stable, but only metastable, then a lower energy vacuum could theoretically appear and expand at nearly the speed of light, changing the laws of physics inside it. This is deeply speculative, and there is no evidence it is happening. It would be an ending not of slow fading or tearing expansion, but of a sudden change in the underlying state of reality. Then there is the Big Rip, the most dramatic of the expansion endings. The Big Rip depends on phantom energy, dark energy, with an equation of state value less than -1. In such a universe, dark energy density increases as the universe expands. The more space expands, the stronger the dark energy becomes. The stronger it becomes, the faster expansion accelerates. The faster expansion accelerates, the more dark energy grows. A runaway. An ending where expansion does not merely separate distant galaxies. It eventually overcomes every binding force. At first, the effect would be almost impossible to notice locally. Galaxies would still hold together, stars would still burn, planets would still orbit. Life, if it existed, might continue under familiar skies. But on the larger scales, the expansion would grow more aggressive. Galaxy clusters would begin to lose their grip on one another. The spaces between clusters would stretch with increasing force. Large-scale structure would dissolve. The cosmic web would come apart. Filaments that once connected galaxy clusters would thin and separate. Superclusters, already often not fully bound in the strictest sense, would lose coherence. The universe's grand architecture would unravel from the outside in. Then the effect would reach smaller scales. Galaxies would become vulnerable. A galaxy is held together by gravity, stars, gas, dark matter, and black holes bound in a common structure. In a Big Rip scenario, the accelerating expansion eventually becomes strong enough that even this gravitational binding cannot hold. Stars would no longer remain in galactic orbits. The galaxy would disperse. Spiral arms would lose meaning. Galactic disks would cease to be systems. The Milky Way, or whatever future remnant of it existed, would be torn open by the expansion of space. Stars would drift away from one another, not as ordinary ejections, not because of close encounters, but because the expansion of space itself would overcome the galaxy's gravity. The universe would become a field of separated stars. Then, later, even star systems would fail. Planets orbit stars because gravity binds them. Earth orbits the Sun because space-time is shaped by the Sun's mass, and because Earth moves along its path within that gravitational relationship. In a universe approaching a Big Rip, dark energy's effective repulsion would grow until it overwhelms the gravitational binding of planetary systems. Planets would leave their stars. Moons would leave their planets. The ancient order of orbits would break. The solar system, if it still existed in any recognizable form, would come apart. A planet would no longer return along its orbit. A moon would no longer circle its world. The quiet clockwork of gravity would fail. There is something especially haunting about this stage. Galaxies are already immense and distant from ordinary experience, but solar systems feel more intimate. A planet orbiting a star is one of the most basic images of cosmic order. The Big Rip imagines even that order undone, but it would not stop there. As the runaway expansion approached its final moment, it would reach the scale of planets and stars themselves. Objects that are held together by gravity, pressure, and internal forces would be stretched beyond stability. Planets would be torn apart. Stars would be disrupted. White dwarfs, neutron stars, and other compact remnants would face the increasing violence of expansion. Then matter itself would be threatened. Atoms are not held together by gravity, but by electromagnetic forces. Atomic nuclei are held by the strong nuclear force. These forces are vastly stronger than gravity on small scales. Under ordinary cosmic expansion, atoms do not expand. You do not grow larger because the universe expands. Earth does not expand because space expands. Bound systems resist expansion. But in the Big Rip scenario, dark energy grows without limit. Eventually, the expansion becomes strong enough to overcome even the forces holding atoms together. Electrons would be stripped from nuclei. Then, in the final extreme, nuclei themselves, and perhaps even more fundamental structures, would be torn apart. The universe would approach a final singularity of expansion. Distances would grow without bound. The scale factor of the universe would become infinite in a finite time. The fabric of cosmic structure would be erased not by collapse, but by runaway stretching. This is the Big Rip, a possible ending in which everything bound becomes unbound. Clusters, galaxies, stars, planets, atoms, all separated by the accelerating expansion of space. But again, it must be remembered, this is not known to be our future. It is a scenario, a warning written in equations, a possibility that depends on the true nature of dark energy. If dark energy is a cosmological constant, the Big Rip does not happen. The universe expands forever, but bound systems remain bound, and the far future is closer to the Big Freeze. If dark energy changes in another way, the future may differ again. The universe may be more subtle than any simple ending. The fate of everything depends on the unknown physics of the emptiest spaces. This is one of the most mysterious facts in all of science. The future of galaxies, stars, planets, and matter itself may depend on something we cannot yet fully explain. The energy of space, the behavior of dark energy, the pressure of the vacuum, or some field that changes across time. The universe began in a state we cannot completely understand. It may end because of a force we do not completely understand. At the beginning, our knowledge fades into the first fractions of a second. At the end, our knowledge fades into the nature of dark energy. The story is framed by mystery on both sides. Between those mysteries came everything we know: particles, atoms, stars, galaxies, planets, life, memory. The Big Rip, whether real or only possible, gives a particular emotional shape to the end. It is not the cold patience of heat death. It is not the reversal of the Big Crunch. It is a future where expansion becomes the dominant fact at every scale. A universe that began by expanding from a hot, dense state ends by expanding so violently that structure itself cannot survive. There is a strange symmetry there. Expansion at the beginning, expansion at the end. But they are not the same. The early expansion allowed the universe to cool, form matter, release light, and build structure. The Big Rip expansion, if it happened, would undo structure. The first expansion made time for galaxies. The final expansion would take galaxies apart. Creation by expansion. Destruction by expansion. A beginning and an ending written in the stretching of space. Yet the universe between them is not meaningless because it ends. A star is not meaningless because it burns out. A life is not meaningless because it is finite. A galaxy is not meaningless because it changes. The age of stars matters because it exists between darknesses. The universe's beauty may be inseparable from its impermanence. If the future is the Big Freeze, then the cosmos fades into cold silence. If the future is the Big Rip, then it ends in runaway separation. If the future is something stranger, then our current science has not yet named it properly. But in every case, the present universe is temporary. The Milky Way as we know it is temporary. The sun is temporary. Earth is temporary. The night sky is temporary. Even the constellations are temporary, their shapes changing as stars move through the galaxy. The galaxies visible to telescopes are temporary arrangements of stars and dark matter. The cosmic web itself evolves. Nothing in the universe is frozen outside time. The story from the Big Bang to the Big Rip is therefore not just a story of beginning and ending. It is a story of transformation. The first universe was hot and dense. Then it cooled. It made nuclei. It made atoms. It became transparent. It went dark. It formed stars. It made galaxies. It forged heavy elements. It built planets. It gave rise to life. It discovered itself through conscious beings. And then, eventually, it changes again. The far future is not one moment, but a sequence of disappearances. First, the bright blue stars vanish as star formation declines. Then galaxies redden and age. Then sun-like stars leave the main sequence. Then red dwarfs dominate the light. Then even red dwarfs fade. Then stellar remnants cool. Then black holes remain as the deepest gravitational objects. In the Big Freeze, black holes may eventually evaporate through Hawking radiation over unimaginably long timescales, though this process has not been directly observed. The smallest black holes would disappear first. Supermassive black holes would last for times so vast that writing the number barely helps the mind. Then, after they too fade, the universe would be left with extremely low-energy particles, radiation, and darkness. This is a future almost empty of events. Time would still pass, but with little to mark it. The universe would become a cold, thin whisper. In the Big Rip, the sequence is shorter, once phantom energy becomes dominant enough. The end comes not by exhaustion, but by acceleration. Structures are torn apart in order of scale from largest to smallest. The horizon shrinks. The ability of one region to affect another collapses inward. The cosmos loses connection with itself. A universe is not only made of things, it is made of relationships. Stars related to galaxies. Planets related to stars. Atoms related to nuclei and electrons. Galaxies related to clusters. Regions related by light and gravity. The Big Rip is the breaking of relationships, the final isolation of every part from every other part, the ultimate loneliness of expansion. This is why the image is so haunting, not because it is violent in a familiar way, because it is separation made absolute. The universe becomes unable to hold itself together at any scale. And then, at the final limit, the equations reach a boundary. Just as the beginning of the universe leads to questions our physics cannot fully answer, the final Big Rip would lead to an extreme where ordinary descriptions fail. Infinite expansion in finite time is not something human intuition can hold. It is not an event one could watch from a safe distance, because all distances and all observers would be part of the process. There is no outside to the universe. No place beyond the rip from which to see it happen. Cosmology always returns us to that truth. We are inside the thing we study. At the beginning, there was no outside space into which the Big Bang exploded. At the end, there would be no outside place from which to observe the last expansion. The universe is not a stage inside a larger room. It is the room. It is the stage. It is the history. It is the distance between every object. It is the changing relationship of all things. The Big Rip would not happen somewhere. It would happen everywhere, but only if dark energy follows that extreme path. The more conservative future, if dark energy remains constant, is quieter. The expansion continues forever. Galaxies beyond the local group vanish beyond the horizon. The local merged galaxy ages, stars die, red dwarfs fade, black holes linger. The cosmos becomes cold and dark. No dramatic final tear, no final collapse, just the long approach to emptiness. This is perhaps more likely under the Standard Model, but the Standard Model itself is still being tested. Dark energy remains mysterious. Measurements continue. New surveys map galaxies across billions of light years. Supernovae, baryon acoustic oscillations, gravitational lensing, the cosmic microwave background, galaxy clusters, and other probes all help refine the story. The universe is still being measured. Its fate is still under investigation. This uncertainty should not be treated as a weakness. It is the honest edge of knowledge. The story of the universe is not a completed book. It is a book with the first chapters reconstructed from ancient light, the middle chapters written in stars and galaxies, and the final chapter still hidden in the nature of dark energy. We know more than any generation before us, but the ending remains unwritten. Not in reality, perhaps. Reality will follow its laws, but unwritten to us, unknown. In the present age, galaxies still shine. The sun still rises over Earth. The cosmic microwave background still hums faintly in every direction. The Milky Way still forms stars. Distant galaxies still send their light across the expanding dark. The future is far away, but it is already implied in the equations. Every star carries an ending. Every galaxy carries an evolution. Every expanding distance carries a future horizon. Dark energy acts quietly now, not tearing apart solar systems, not disturbing planets, not changing daily life. Its effect is seen only on the largest scales across the vast distances between galaxy clusters. But the largest scales determine the destiny of the whole. This is another strange truth. The most important force in the far future may be almost invisible in the present. It does not shape mountains. It does not hold atoms. It does not light stars. It does not bind galaxies. It stretches the cosmic distances between the largest structures, slowly and relentlessly. The fate of the universe may belong to the emptiness between galaxies. What seems empty is not nothing. Space itself has properties. The vacuum may have energy. The expansion has dynamics. The dark between galaxies is not merely a backdrop, it participates in the evolution of everything. At the beginning, space expanded and cooled the universe. In the middle, space allowed galaxies to separate, while gravity gathered matter locally. In the future, space may stretch so much that distant regions disappear from one another. And in the Big Rip scenario, the expansion of space becomes so extreme that even local structure cannot endure. The story has always been about space as much as matter. Matter shines. Space decides distances. Matter gathers. Space expands. Matter forms stars. Space carries galaxies apart. Matter creates complexity. Space sets the horizon. The Big Rip is the imagined moment when space overwhelms matter completely. The expansion wins at every scale. No island remains, no orbit, no atom, only the final runaway of distance. But perhaps the universe will not choose that ending. Perhaps dark energy is constant. Perhaps it evolves and weakens. Perhaps the deepest theory of quantum gravity will reveal that our current categories are incomplete. Perhaps the true fate is not Big Freeze, Big Crunch, or Big Rip, but something for which we do not yet have a name. This too is fitting. The universe began beyond the reach of complete explanation. It would be strange if its ending were simple. Cosmology does not give us a closed circle. It gives us horizons. The particle horizon limits what we can see of the past. The event horizon may limit what can ever influence us in the future. The beginning lies behind a horizon of extreme physics. The ending lies behind a horizon of unknown dark energy. We live between horizons, in the bright middle. In the age when stars still shine and evidence still reaches us. In the age when the universe can be studied. In the age when atoms made in stars can become eyes, instruments, and questions. The universe began in a state without stars. It may end in a state without stars. Between those two starless immensities, the cosmos formed light, and in that light for a while there were galaxies, there were worlds, there was thought, there was memory, there was the ability to ask where everything came from and where everything is going. The Big Rip, as a possible ending, gives one answer. Everything came from expansion. Everything may end in expansion. But the answer is not final, because dark energy remains unknown. The universe is still holding back its last secret. If phantom energy is real, the far future becomes a countdown, though on timescales that depend on its strength. First, the largest structures loosen, then galaxies unbind, then systems fail, then matter itself is torn apart. The end comes everywhere, not as fire, not as ice, but as separation. If phantom energy is not real, the The universe may instead drift into the long night of the Big Freeze. No dramatic tearing, no sudden final moment, just fading starlight and widening distance. Both futures are mysterious. One is a scream stretched across space-time. The other is a whisper fading forever. The true future may be neither. But the thought of the Big Rip reveals something important, even if it never happens. It shows how deeply the fate of the universe depends on laws we are still trying to understand. It shows that space itself is not passive. It shows that the largest and emptiest scales may decide the destiny of stars and atoms. It shows that the cosmos is not only a collection of objects, but a dynamic whole. A whole that began, a whole that evolved, a whole that may end. When we look at the night sky now, we see the universe in its luminous interval. Many stars visible to the eye are already old. Some may no longer exist in the same state, their light still traveling toward us. The Milky Way stretches overhead, a bright band of our own galaxy. Beyond it, through telescopes, lie billions of other galaxies, each with its own history, its own stars, its own dead and living systems. They seem permanent because our lives are brief. But the universe knows longer time. It knows the time for galaxies to form, for stars to die, for clusters to drift, for horizons to close, for black holes to evaporate, for expansion to decide the final architecture. Human time is a spark inside cosmic time, but that spark can understand the flame. It can trace the path from the Big Bang to the first atoms, from the first darkness to the first stars, from galaxies to worlds, from dark energy to possible endings. It can imagine the Big Rip, not as myth, but as a mathematical possibility born from the unknown nature of cosmic acceleration. That is one of the quiet wonders of the universe. The universe became capable of asking about its own fate. In the beginning, there were no questions. Only heat, density, expansion, then particles, then atoms, then darkness, then stars, then galaxies, then planets, then life, then thought, then cosmology. Then the idea that the same expansion that began everything might, in one possible future, tear everything apart. The story is vast and still incomplete. Let us imagine the final sequence one more time, not as certainty, but as possibility. In a universe of phantom dark energy, expansion accelerates more and more. Distant galaxies vanish first, redshifted into darkness. Superclusters dissolve. Galaxy clusters come apart. The cosmic web loses its shape. Galaxies, once held together by dark matter and gravity, begin to unbind. Stars drift into isolation. Planetary systems break. Worlds leave their suns. Moons leave their worlds. Planets fracture. Stars are torn. Matter is stripped to smaller and smaller scales. Atoms lose their structure. Nuclei cannot hold. The universe reaches a final boundary where all distances diverge. The Big Rip. A final unbinding. No center, no edge, no outside. Only expansion carried to its most extreme conclusion. And if that is not our future, then the image remains as a shadow at the edge of theory, a reminder of how strange dark energy could be. The more likely future may be quieter, but no less profound. Stars fading. Galaxies isolated. Black holes wading through unimaginable ages. The universe thinning into darkness. Either way, the bright age is temporary. The universe that began without stars will one day lose them. The great galaxies that now define the sky will fade or pass beyond reach. The cosmic web that grew from tiny early ripples will become less visible to any local observer. The afterglow of the Big Bang will cool towards silence. The story will become harder to read from within the future universe. But now, In this moment of cosmic history, the story is readable. Ancient light still reaches us. Galaxies still reveal the expansion. Stars still forge elements. Dark energy still leaves clues in distance and time. The universe has not yet hidden everything. It is still speaking. Through redshift, through microwave background, through supernova light, through galaxy maps, through gravitational waves, through the chemical memory of stars, through the simple fact that the night sky is full of ancient information. The path from the Big Bang to the Big Rip is not a straight road. It is a widening, a flowering, and perhaps an unraveling. It begins in heat and density. It passes through darkness. It awakens in stars. It builds galaxies, planets, and life. Then it moves toward an ending shaped by dark energy. At the beginning, space expanded. At the end, space may continue expanding forever, or it may transform the universe in ways still unknown. The beginning was not an explosion in space. The ending may not be an explosion either. It may be fading, it may be tearing, it may be collapse, it may be something deeper than any of these. But whatever the ending is, the universe has already done something extraordinary. It has turned simplicity into complexity. It has turned hydrogen into stars. It has turned stars into elements. It has turned elements into worlds. It has turned worlds into living chemistry. It has turned living chemistry into minds capable of imagining the end of time. That is the strange middle chapter we inhabit. Between the first fire and the final dark, between the Big Bang and whatever waits beyond the last horizon, the universe is still expanding. Galaxies are still moving. Stars are still burning. Dark energy is still mysterious. And far ahead, beyond all ordinary time, the final fate remains hidden. Perhaps the universe will freeze. Perhaps it will rip. Perhaps it will change in a way no current theory can fully describe. The last answer is not yet ours. For now, the cosmos continues. The Milky Way turns. The local group moves. The cosmic web glimmers across the dark. The ancient microwave glow fills all directions. New stars form from old clouds. Old stars return their matter to space. Black holes sleep and feed. Planets circle. Light travels. Space expands. And somewhere in the equations of dark energy, somewhere in the quiet behavior of the vacuum, somewhere in the deepest structure of reality, the final chapter of the universe is waiting.